Okay, in this video we'll talk about graphing radical functions. And we're just going to focus on the square root graph. There is a cube root graph that you could figure out similarly, but we're going to skip that. And so the square root is the inverse of the squaring function. When we have a squaring function, when we have a quadratic, the graph is a parabola. So we're going to talk about the graph of a square root, and the notion that it's somehow related to parabolas is going to emerge. But let's first do this just by plotting points. So just make a table here of x and y values. And think about numbers where it's easy to take the square root. So 0, 1, 4, 9. I could actually put in something intermediate like 1/4. The square root of 1/4 is 1/2. Could put in something like 2.25, which is 9/4. The square root of that is 3/2, which is 1.5. And if we plot this, I'm doing this by hand, so it'll be imperfect, but I'll try my best. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. I have a point at 0, 0. I have a point where the x is 1/4 and the y is 1/2. I have a point at 1, 1. I have a point where x is 2 1/4 and y is 1.5, something like so. I have a point at 4, 2, and I have a point at 9, 3. And if I connect these, might not be obvious from my hand-drawn graph, but if I connect these, what I'm actually getting in my graph is half of a sideways parabola. There's this phantom half down here that I'm not graphing. But we'll notice, oh yeah, that's actually the shape of a parabola, only it's sideways this time. So we'll just note it is the upper half of a sideways parabola. So if you remember that fact, and you remember the absolute 3 easiest points, just the 3 easy small numbers that you can take the square root of. If you remember those 3 points and that the general shape is a sideways parabola, you'll be fine. It doesn't have to be perfect. And we'll just remind ourselves that all of the normal transformation rules apply. So if we throw a negative in front of a function, as usual, it turns it upside down. So if I were to graph this, it would look like what we just graphed before, but upside down. So it would be the bottom half of a sideways parabola. This was a typo. It was supposed to have the negative inside. This is going to be a left-right flip. That's the general pattern when we put a negative inside something. So it'll be half of a sideways parabola, but it'll be going to the left instead of going to the right. One thing I should comment about on this graph is that this graph only exists in the first quadrant. We really can only make sense of this if both x and y are positive. So we'll also note that. For this plain version of y equals root x, the graph is only in quadrant 1. We can only take square roots of positives or 0. And when we take that square root, we get a positive or 0. Right, this is the square root function, which only gives us one answer, the positive answer. Okay, if we multiply by a number, that adjusts the height. If a is bigger than 1, it gets taller. If a is smaller than 1, it gets shorter. So for example, just for concreteness, if I had y equals 2 times root x, be the same general pattern, but twice as tall. Instead of a point at 1, 1, I would have a point at 1, 2. Instead of a point at 4, 2, I'd have a point at 4, 4. So it would still be half of a sideways parabola, but it would be taller. We know that this shifts horizontally. So for example, if I had y equals the square root of x minus 5, it would be the same graph, but instead of starting at the origin, it would start at 5, 0. Adding or subtracting outside the function, outside the radical, shifts vertically. So it would look something like so, assuming that k is positive. So if we go step by step, we can draw these transformed versions of the square root. So I will do the first one, and then I recommend you pause and try the second one. And let's just do this step by step. So we would start with y equals root x, and at every step just draw the 3 easiest points and trace where they go after the transformation. So the 3 easiest points on the original version are at 4, 2, 1, 1, and 0, 0. Then what I could do is I could multiply that by negative 2. That's going to turn it upside down and twice as tall. So effectively, I'm multiplying each y coordinate by negative 2. So I had a point here where the y coordinate was 2. If I multiply that by negative 2, I get negative 4. So I'd have a point at 4, negative 4. Here, when x equals 1, I have y equals 1. Multiply that by negative 2, and I get 1, negative 2. This first point, if y equals 0, multiplying that by negative 2 still keeps it at 0. So it is upside down and taller than it used to be. And then finally, that plus 1 inside the function is going to shift left by 1 unit. So I had a point here at 0, 0. If I shift that 1 unit to the left, it's now at negative 1, 0. I had a point at 1, negative 2. If I shift that to the left, it's at 0, negative 2. Have a point here at 4, negative 4. If I shift that 1 unit to the left, it is at 3, negative 4. And I connect them like so, and this is my graph. So try to do the same things with this example. Start with y equals root x. Draw the graph and label the 3 easiest points. Then just adjust to see what happens with your 2 transformations. All right, so we already have what the original looks like over here, so I won't redraw that. If I do y equals root negative x, that's a left-right flip. So 0, 0 would stay the same place. 1, 1 would now go to negative 1, 1. And 4, 2 would go to negative 4, 2. That minus 2 on the outside would shift everything down by 2 units. So this point at 0, 0 would shift down. This point at negative 1, 1 would shift down. This point at negative 4, 2 would shift down. So when I shift down by 2 units, I'm just subtracting 2 from every y coordinate. These would be my 3 easiest points, and I just reconnect them. Same transformation rules we've had all year, just in a new context. Quick little note here. We haven't done a ton with multiplying inside the function. It gets a little tricky. But occasionally you might notice that if you have an extra coefficient inside, you can apply some factoring. And we can use a radical rule to say, oh, this is actually the square root of 9 times the square root of x minus 2. So there's a way to realize, oh, if I just rearrange this algebraically, I can better understand what's going on. Instead of thinking about multiplying by 9 inside, I can think about multiplying by 3 outside. And that might help you graph better. And then just a reminder that thinking about graphs can help us solve equations. If you wanted to solve this equation, maybe one option is to just graph these things. You could graph y equals x plus 1, or square root of x plus 1, which would look something like so. You could graph y equals 7 minus x, which would look something like so. And you could use intersect on your calculator. It's nice to know the algebra, but sometimes if we want to figure out where two things are equal, visualizing the graphs is the best way to go. All right, that's it for this section.